Okay, so we start our session. We are at around page 17 and 18. So feel free if you need to refer to the textbook. Okay, so we have been talking about unbiasedness. So if the expectation of the estimator is equal to the true value, then it's called unbiased. And unbiased is a property that we like to have. Okay, so uh, then we also talk about the definition of bias. So if you have a, a constant deviation from the true value, for example, this is the expectation of the estimator, and then the true value, if you take the expectation is always constantly equal to the true value plus a bias B, then that B is called a bias. And notice that B is written as a function of theta. The reason is bias uh, bias actually depends on the value of theta. So it's a concept. So let's see if uh, you have a bias B. It's actually a function of theta. In other words, it could be different from different values of theta. In some value of theta, the bias may be smaller. In some values of theta, it could be larger. So bias is dependent on theta. Okay, so we can also write bias as effect of theta hat minus theta. So let's call the bias. Okay, so then let's continue to the next subsection. So minimum variance criteria. So in search for optimal estimators, we need to adopt some optimality criteria. So in other words, when we are talking about optimal, it's always related to some kind of objective, right? Ob objective function. So later on, we will talk about different objectives such as likelihood as the objective function. But right now, uh, we are going to adopt uh, minimum variance as the objective function. So we need to adopt some kind of optimality criteria. Then a natural one is the mean square error. Mean square error. So we define mean square error as mean square error is a function of theta hat because you could have different designs for theta hat, and therefore it's a function of theta hat and then equal to expect of theta hat minus true value, and then you take the square and then you take the expectation. That's called the mean square error. The square comes from here, so it's the error square, and then take the expectation. That is called the mean. So mean square error. Okay. So this measures the average mean square deviation of the estimator from the true value. Then unfortunately, adoption of this criteria leads to unrealizable estimators. Ones that cannot be written solely as a function of the data. To understand the problem, we first derive the MSE as something like this. So we take a look at the derivation. Expect of theta hat minus E theta hat plus E theta hat minus theta, and then take the square. So this is the temporarily as a dummy variable, right? Because originally you have theta hat minus theta. Now we come up with the dummy variable e theta hat, and then you minus that, you plus that. So dummy variable actually cancel out with each other. But of course, we are not going to let them to make it cancel. We are going to do this and this separately. So if we have expect square, expect theta hat minus theta square, then um, the square of this term comes to here, right? And then theta hat minus e theta square is like this, right? Think of this as this way. Okay, let's do it carefully. You have a plus b square, right? This is a and this is b, so you have a plus b square, and it's equal to a square plus 2 b plus b square, right? So it's this term square plus 2 multiplied by this term and this term, that is 2ab, and then b square, which is this term square. And this, the square of this term comes to here. The square of this term goes to here. And the cross term is this minus this multiplied by this minus this. Take the expectation. And that power is 0. Okay? So the cross term is equal to 0. As a result, it disappears. It disappears. So if we see this, then we will see that only that square, which is variance sigma square, and this square, which is aspect of theta hat minus theta square. Okay, and this is the variance of estimator theta hat, and this is aspect of this minus that. If we recall a little bit, that is the bias aspect of this minus that, and aspect of theta hat minus theta square, that is bias square. It shows that the MSE is composed of errors due to the variance of the estimator as well as the bias. So the MSE is in fact the variance of the estimator as well as the bias. And then the bias depends on theta, but the theta by definition is supposed to be unknown, right? We have to be clear about the setup of the problem. The setup of the problem is that the theta is unknown because this is what we are looking for, right? Theta is what we are looking for. So it is not supposed to be available. It's unavailable. Okay, so as a result, if we are looking at MSE, it's related to something that is not available, then at least at the surface, we will not be able to derive MSE at this point because of the unavailability of theta. So as an example, for the problem 2.1. So 2.1 is, let's see the model again. 2.1 is this model. And we want to find A. We want to find A. Okay. So we consider the modified estimator A total equal to 1 divided by n summation xn, and adding a multiplier A, adding a multiplier A in front of it. So for some constant A, we will attempt to find the A which results in the minimum MSE. Okay, we find the A that results the minimum MSE, because A is, recall that a lot of things can be by design, right? 就是这个 estimator 本身是一个设计的问题，所以 A 是可以设计的。A is on our design. It's not some kind of magic number. It can be adjusted by our design. So we will attempt to find the A which results the minimum MSE. Then you take the expectation of A delta, and this term converges to A, right? So if you take the expectation, it's going to be small a multiplied by capital A. So it's like this. And then variance of A total is sigma squared n multiplied by A squared. The square of this has been proven. We did it before. It's sigma squared divided by n. And you have extra A, and then extra A comes in as a square. So you have A squared, sigma squared divided by n. So we have from 2.6, let's see, 2.6. Yeah, I'm sorry, 2.6 is here. So we have from 2.6 variance of sigma hat, and variance is like this, so variance is like this. And then another term is bias, right? The bias square theta, bias square theta. So the bias is A minus 1. And then how come? Uh, let's see here. You have expect of theta hat, right? So let me do it one more time. This variance theta hat is variance A A dot delta. That is down here. So this term is equal to A square sigma square divided by n, right? And that goes to here. And then E theta hat is E A delta, right? That's E theta hat minus A, and then remember you have a square, so you have a square. Then it becomes what? It becomes A minus A, right? So it becomes A minus A, and then square. and then it goes to here, right? You take the a out, you take the a minus 1 out, you get a minus 1 square, and then a square. Okay, so uh, eventually you get to the point of a squared sigma square divided by n plus a minus 1 square a square. Then differentiating because we want to find a mean. So you recall what we learned in calculus. We take the differentiation and then we would attempt to set it to 0, right? We recall first order derivative, right? We take the first order derivative of a function and then set it to be equal to 0. And that gives us the x value that generates the minimum or maximum of the function. Okay, this is a common technique. And later on, we will use that technique too to apply to likelihood. We will apply this to likelihood later on. But now we do it for MSE with respect to A. Okay? So the MSE A hat with respect to A. So you take the derivative of this. It's going to give you 2a sigma squared divided by n. Right? Derivative of this. And then take a derivative of this. It's going to give you 2a minus 1a squared. So that one goes to here. And then upon setting to 0, 就是把一个函数的一阶函数把它做一阶微分，然后再设成0。这个是我们常常找最大值最小值的一个微积分的方法。如果不清楚的话，可以稍微再 review 一下微积分的部分。Okay, so we solve it, then it yields the optimal value, which is equal to this. So you set it to 0. And then solve for a. So f optimal is equal to a squared divided by a squared plus sigma squared n. So it all look good and reasonable up to this point. But the problem is, well, if we come back to the problem itself. Right? So as a toy problem, let's look at the details. Just for one time or two times, then later on you get used. You'll be more used to it. We are trying to find a, but a is a parameter to be estimated. So the a is supposed to be unknown. If a is available, then the problem doesn't exist at the first place, right? 如果 a 知道的话，这个问题根本连算都不用算了。所以问题原本的设定就是 a 就是不知道的。Okay, so so if we solve for small a, right, small a, and it gives us a function of capital A, but capital A is unknown. Capital A is supposed to be unknown. Then we have a problem, right? We have a big problem because A is not available, and ultimately we will not be able to get A optimal. We are not able to get it because capital A is supposed to be unavailable. So it is seen that unfortunately the optimal value of A depends on the unknown parameter A. The estimator is therefore not realizable. In retrospect, the estimator depends upon A, since the bias term is a function of A, right? So if we look back for this, it's a function of theta. In our case, in our example, it's the capital A. So if it's a function of A, then it's supposed to be unavailable. which any criteria which depends on the bias will lead to an unrealizable estimator. Okay? But in some cases, it may be available by coincidence. Okay? So uh, from a practical point of view, the MSE estimator needs to be abandoned. An alternative approach is to constrain the bias to zero. Right? We constrain. This is what we often do. We constrain the bias to be zero. Meaning what? Meaning this is an unbiased estimator. Unbiased. Unbiased estimator. And find the estimator which minimizes the variance. Such an estimator is termed the minimum variance unbiased estimator. NVU. So that NVU is an important concept. It's an important concept. So such an estimator, we call it, let's see again, minimum variance and then unbiased, as opposed to previously we say minimum variance only without unbiased. We call it, well, we'll see again, minimum square error only, minimum variance criteria. We didn't say unbiased, but now we add something abstract that is unbiased. Then the unbiased, if we see the unbiasedness, then this term will be zero. This term will be zero. Then it will be to minimize the variance of the sigma. I'm sorry, to minimize the variance of theta hat. Okay, so the MSE of unbiased estimator is just the variance. Minimizing the variance of an unbiased estimator also has the effect of concentrating the PDF of the estimator error about zero. The estimation error will therefore to be less likely to be large. Okay, so let's take a look at potential cases, possible dependence of estimator variance with data. So this is the variance of versus theta. Remember, I want you to pay attention to that this is theta hat. Remember, this is the theta hat, meaning that it's an estimator. And this is the theta, meaning that it's the true value. This is the true value. So it's not a, it's the variance of the estimator versus the true value theta. It's not the variance of theta hat versus the estimator value theta hat. It's not like that. Okay, I want to emphasize it's not this. On the horizontal axis, it's not theta hat, it's theta. Theta is a true value, but unknown. Okay, so we have variance theta hat and then versus theta. And there are some cases where you see theta 1, this is bio design, and theta 2, and theta 3. And you see that in this case, this one is larger than this one. So what that means is theta 1 is uniformly better than theta 2. Theta 1 is uniformly better than theta 2. Theta 2 is uniformly better than theta 3. As a result, if you compare all of them and then find out theta 3 is the uniformly better than all the others, then it's the NVU. It's MVU. It's a minimum variance unbiased estimator. Of course, the unbiasedness is not discussed here, but we assume that theta 1, theta 2, and theta 3 are all unbiased. Okay, so that is the MVU. But in some cases, you have theta 1 uniformly higher than theta 2. And then theta 3, it's higher here in this region, but theta 3 is lower in this region. As a result, theta 3 is better in this region. Theta 2 is worse than theta 3 in this region. As a result, we will not be able to say any one estimator is uniformly better than the others. We will not be able to say that. As a result, we will say that it's no MVU. There's no MVU estimator because some are better than others in some region, for example, this region, and some are better than the others in another region. As a result, but uh, theta is supposed to be unknown, so who knows where it is, right? No one knows where theta is. So we will not be able to say uh, any one is better because theta could be here, theta could be here, theta could be here, right? It could be anywhere. Okay, so this is some of the situations we may encounter in some problem setups. So we want to be aware that MVU may exist and there is a way to find it or it may not exist. Okay.